Kia ora, Year 11 and 12. Here's question 3b from this year's calculus paper. So this is a classic optimisation problem about a cardboard box. Well, I guess we're assuming it's a cardboard box. It's some kind of parcel and it's in the shape of a rectangular cuboid. We're told that the parcel has got a square cross-section and the sum of the length of the cuboid and the perimeter of the square cross-section has to be 100 centimetres. And that diagram is not to scale, but it's actually not too bad. We have to figure out the maximum volume of the parcel. So as usual, I'm going to start by drawing a diagram, and the diagram that I'm going to draw, because I've got the 3D box already drawn, is the diagram looking at the square cross section, and I'm going to call the dimension of each of those sides W. Now I know that they're all W because I'm told that that there's a square cross section, and the sum of the length of the cuboid, which is this bit here, and the perimeter of the square cross section has to be 100 centimetres. So we're setting up a constraint here, and the constraint goes like this. 100 is equal to the perimeter, so 4W, plus the length, which for some strange reason I have called H instead of L, right? And now we have to figure out, what are we trying to maximise? Well, we're trying to maximise the volume of the parcel. So the volume of a cuboid is length times width times height, but in our case, length and width, these two things are the same, right? This H is different. So V is equal to W squared H. Now, as you'll know from doing other optimization problems, the issue with this is that we want to differentiate to find a maximum, but we can't differentiate that because it's a function of two variables. So we have to use our constraint to find a way to replace one of them. And the obvious one to replace here is to take H and get it in terms of W. So we have 100 equals 4W plus H, giving me H is equal to 100 minus 4W. That gives me an expression for V of W squared times 100 minus 4W. We can expand out those brackets and get 100 W squared minus 4W cubed. Differentiating, I get dV by dW, which is 200W minus 12W squared. And we know that that has to equal 0 for a maximum or a minimum. And at the end of this question, we have to show that we found the maximum and not the minimum. Right, so what do I have to do? Well, I have to set this equation equal to 0 and solve it. So this is very straightforward. At this point, we've got, what can I take out? I can take out a common factor of 4. So I've got 4W into 50 minus 3W equals 0. So two solutions here. W equals 0 or W equals 50 over 3. So that's 16.66666, but let's leave it as a nice exact answer as a fraction for now. Right, so we can tell which one of those is going to be the maximum. It would be pretty stupid if it was 0, but we're not going to say it would be stupid. We can think about the curve that we've got. Well, V is a negative cubic, right? So it has a shape of down, up, down. So we know that this point is going to be the first one, which is W equals 0, and this point is going to be the second one along, which is W is equal to 50 over 3. So it's a maximum here. The other really easy way to do it is to do the second derivative test. So there's my first derivative, 200W minus 12W squared. So the second derivative is 200 minus 24W. And we can substitute in our values. So the second derivative evaluated when W is 50 over 3 works out to be 200 minus 8/50s, which gives us 400. So that's negative 200, and that's negative. So we've got a local maximum at this point. But what I haven't done yet is what I was asked to do, which is to figure out what is just going back up to read the instructions. We have to find the maximum possible volume of the parcel. So we have to take our value for W, we have to work out H, and we have to substitute it all back into V. Something weird's happened with my window frame here, so hopefully you can see this. Let's see, h is equal to 100 minus 4w, so that's minus 4 times 50 over 3. So that gives me 300 minus, so that gives me 100 over 3. So the volume of the box, which is w squared h, works out to be 50 over 3 squared times 100 over 3. And when we work that through, we get this exact answer, which looks very silly, or more real-lifely, new word, we get 9,259.3 centimetres cubed, and that's just rounding to 1 dp, which seems like a sensible level to round to. It's one significant figure more than the dimensions that I've got. Okay, so I think that's actually a very easy excellence question. I know that most people doing level 2 don't love optimization problems, but it really doesn't get much more obvious and straightforward than this. So if you're watching this and you're sitting level 2 next year, make sure you do heaps and heaps of examples of problems like this. The Theta textbook has got tons of them in its application section.